Welcome to NASA Edge.
An inside and outside look at all things NASA.
Joining us today is Chuck Taylor, who's the project manager for vertical solar array technology, which involves technology on the moon. Thanks for being on the show today.
Thanks for having me.
You know, Chuck, it's really interesting because with Artemis and all the efforts NASA's making to send missions to the moon, got some real challenges ahead of how we're going to do this. And you're right in the thick of it. What are some of these challenges that we're facing as we look at putting that permanent outpost on the moon?
Well, I think obviously power is the number one concern. As you go to an outpost and you have to think about keeping your astronauts alive, generating oxygen, water, or if you want to do your research while you're on the moon, you need power. It's a fundamental first block that you need before you do anything very large or you stay for long. The only other way you can go about it is storing your energy in batteries. And we all know that batteries are very heavy, that it takes a lot to get them to the surface of the moon, and then they need to be regenerated in the end because they don't generate their own power. And so in the end of the day, whatever we do, we need to be able to generate power on the surface of the moon.
Through Artemis, they're also going to be exploring different parts of the moon where they have to get power to those locations like the craters.
You bring up a great point. Okay, the first step is power generation. We need to be able to convert the sun's energy into electricity. That's what our solar arrays do. But the second thing we need to do is distribute that. And when you're on the moon's surface and you're generating in one location, whether you're going 3 or 4 kilometers into a crater, or you're going 500 meters over to a habitat, you need to be able to get that power there. On Earth, it's so easy. We have this incredible infrastructure of long-haul electrical grid that takes high voltage power, sends it over cables, you transform it into what you use in your house, and it all works out very well. That's been developed over 100 years or more. On the moon's surface, if we generate that power, we still have to either have our customers come to us, literally to the base of our solar array to get the power, or we have to string a cable to them, or we have to think about doing something else like power beaming in order to get that energy to where it's needed. So we have ways to do it, but you started with, and it comes down to a very fundamental 2-part problem. Generate the power, distribute the power.
And of course, we're really talking about a scale issue because obviously we may be at a point where we have large solar panel farms on the moon someday. But right now we're talking about a lunar outpost and where we have very specific need and efforts that we're undertaking that require something a little bit more mobile. And that's where vertical solar array technology comes in.
Yeah, well, when we started VSAT, there were a couple critical issues. One is the plan was to go to the south pole of the moon. We want to go to the south pole of the moon, much to what Franklin was alluding to earlier, in that we want to look inside craters because there's some excellent science there. And there are permanently shaded regions who have never seen the sun. And because of that, there are volatile chemicals that may be the perfect place to generate oxygen and water. But the flip side is the sun, even when you're not in the crater, is always at a very low grazing angle. It gets obscured behind hills and little rock outcroppings, etc. And so the light is intermittent if you're right at the surface. And so the purpose of VSAT is to elevate the solar arrays themselves 10 meters off the deck so that when you're up that high, you have almost continuous sunlight even during the lunar winter. You'll have these periods where you will actually be in the dark for 4 days, but that's a far different amount of energy you have to store than if you were out at the equator, say, where you would have to store energy for weeks on end in order to make sure you survive the night. We knew we had built solar arrays in low Earth orbit. We knew we'd taken solar arrays in exploration of the planets right outside of the Earth's domain. We had never done it in a gravitational field, though. And that's one of the real problems that we encountered with VSAT, is everywhere that we had flown solar arrays in space before, they had been in 0G. We wanted to be 10 meters off the ground. Our mast at the end of the day is 20 meters because we have to have the solar array blankets come down. So you needed to put a mast 20 meters up in a gravitational field autonomously. And so this became the very fundamental issues we had to address within this project. And so what we did is we created a government reference design, how we thought we would do it if we were left to our own devices. And then we asked industry. We said, you guys go out and tell us how you would do it. And we gave them our design as a jump-off point. About a dozen companies came back with different designs for how they would go about building the lunar power architecture. Out of that group of a dozen, we selected 5 for studies. And after we had looked at these first level studies where they actually gave us their design, their blueprints for how they would put together the system, their trades that they did all their analysis on why they thought their designs were good, we chose 3 of them, and we took those 3 vendors and we asked them to build prototypes.
So Chuck, tell us about the 3 companies you guys eventually settled on to develop VSAT technology and their proposals.
Well, at the end of the day, we selected Astrobotic, Honeybee Robotics, and Lockheed Martin to develop their versions of a VSAT system. All 3 of them used technologies that had been either completely demonstrated in zero-G or hypothesized in Honeybee's perspective for the lunar surface. And all 3 looked very interesting. They all had their unique characteristics. And we wanted to give them a chance to display what they could do to design this system for us.
We went out to Honeybee and talked to Dean Bergman about their VSAT technology that actually evolved from something they already had in-house. Let's take a look. We are here in Altadena, California at Honeybee Robotics, one of NASA's commercial partners that designs and builds unique solutions for the agency. Honeybee has answered NASA's call to create their version of vertical solar array technology. Dean, can you first explain to me Honeybee's design of VSAT?
Yes, of course. So our system is built out of a couple of modules. The main piece is the central tower, which we call Diablo. What it is, it's sheet metal that wraps up and self-constructs on the moon itself to create a tall tower to hold up the solar rays. Then what you can see is on the top, there's a head that holds 2 arms that fold out and extend and then drop down 10 kilowatts of solar ray blankets. The blankets themselves are kind of like a Venetian blind type system where you use cables and pulleys to release them and bring them back up. And then there's other features such as stabilizing legs and dust-tolerant connectors for connecting to rovers. The solar arrays themselves were provided by a company called Empower, who we partnered with for the VSAT program.
Now, Dean, this is a pretty robust test article. Did you have any part of this already created, or was this all put together from scratch for VSAT?
That's a good question, because we're not known as a power company, but what we have is a lot of robotic systems that we can repurpose. So while we hadn't done this exact thing, most of the systems are derived from other pieces of technology. So the center tower itself, Diablo, was actually a drill to start off with. So we had a much smaller system that would go down into the lunar surface 3 meters to deploy payloads down into the lunar surface. But what we realized is we could flip it around, make it really big, and it would see very similar forces. And so we could create this tall tower on the moon.
This is a very unique design, the sheet metal with the rivets. Can you explain a little bit more about how that works? Because it's kind of mind-boggling to me.
Of course. So, when we were selected to do this, I think NASA had seen a lot of solutions that were the solutions that you would expect, like a boom that would unroll, similar to what happens on the ISS, or a telescoping boom. With all of these solutions, we saw significant issues. You're in a gravity environment, which makes it very difficult. Keeping something straight when you're unrolling it is a very difficult thing to do. If you have surfaces that are rubbing up on each other and you're in a dusty environment, which we are, then that can cause an issue and can get things jammed. So what we have here is something that eliminates all of those issues, right? It's just this sheet with holes on one side and rivets on the other. So when it wraps up on itself, it just pops the hole into the rivet. And what's interesting about it is that it doesn't actually rotate. So this top part does not rotate as you go up, which is very helpful when you're trying to track the sun and deploy it in an orientation that you understand. But it was also designed so that it could come apart again. So it also retracts and the rivets come out of the holes so that it can fold up so that you could redeploy it. Part of the goal of this was to survive for 10 years. And in the surviving for 10 years, we also need to redeploy it up to 10 times so that you could set it down, it could deploy, you could use it to create the 10 kilowatts of power that you need, and then you could stow it again, move it to a different location, and redeploy it over there.
Outside of NASA, do you see any other uses, potential uses for something like this?
Yeah, good question. I definitely do. In space in general, I think there's a lot of applications for it. We have been a part of other programs where we've looked into some of these other applications, like a tall tower on the moon for deploying payloads to a tall height. If you need PNT or comms or floodlights or laser power, all of these different things, you need them at a height that you can then distribute to the moon. And this is a very scalable system. So while this one is about 18 meters tall, we can do one that's about 100 meters tall to get a much wider angle. You can do the same thing on Earth too. We've demonstrated this, that we can deploy it in the terrestrial environment. So if we're in a remote location and you needed, say, a cell phone tower or a comm system, you could deploy it out there pretty rapidly and then fold it up again and take it to the next spot.
Chuck, as you heard in the interview, I thought that Honeybee's design was very robust. It was massive, but it really looked like it worked and it was built upon technology that has already been demonstrated.
Yeah, and they were super proud of it, too. I mean, we walked into their lobby, and they have the VSAT prototype right there in all its innovative glory.
All its glory, yeah.
It's a quite impressive piece of technology.
Now, they have deployed, retracted, and did some environmental tests on that. What data did you get from Honeybee, and what are the next steps for them?
Well, I think success is the first data point. They successfully deployed and retracted the system over 10 times, which is what we wanted them to show. They demonstrated that they could do it on a sloped terrain. They did multiple deployments and retractions. So they've proved their technology is at what we call TRL6, technology readiness level, which is the step before you go to flight. It's been shown to work in a relevant environment, which for us was the moon's gravitational field and vacuum, and the temperature extremes, So it's shown that it can do that. Now, this is the electromechanical system that encompasses their mast and deployer and their solar arrays. And so their next steps going forward is to build the rest of the system, the thermal management, the computers that take care of commanding, data handling, communication with the outside world. All those things are yet to be built, and they would have to bring that together before we could do a flight demonstration. Mm-hmm. But that would be the next step for them. On their part would be the design, and hopefully we envision in the future taking a VSAT of some caliber from one of our vendors, or maybe somebody who comes in fresh, and take that to the moon and demonstrate it in action.
What a great opportunity for Honeybee to find themselves at TRL6 after testing in the thermal vac chamber. We had a chance to actually go talk to John Landerneau and the team at Astrobotic as they were getting ready to go into the thermal vac chamber for their test. Quite an impressive scene. Let's check it out. John, before we get to VSAT, just how cool is it that we're in the control room for the vacuum chamber here at Johnson Space Center, where lots of historical tests have taken place, and now we're going to test something from Astrobotics. How's it feel?
Yeah, it's absolutely incredible. The kid inside me is really excited. So this chamber specifically goes back to the days of qualifying the Apollo command module. Very recently, the James Webb Space Telescope spent a lot of time here being qualified for its space mission, and to have Astrobotic on site doing our technology as well, it's very exciting.
Tell us, what is Astrobotic proposing for VSAT?
So Astrobotic, we consider ourselves mobility experts, and we partnered with Redwire there's success with the rollout solar array program to produce the electricity required to satisfy the requirement. At Astrobotic, we have developed what we call the Astrobotic Mobility Platform, or the AMP. That, together with the ROSA from Redwire, produces what we're calling the Volt, the VSAT optimized for lunar traverse.
Well, considering all these things that you're developing for VSAT, you have to undergo a lot of tests. Tell me about the tests that are needed to actually demonstrate success for your program.
Sure, we have 4 major test campaigns associated with this contract. The first one we just most recently successfully completed at Glenn Research Center's Slope Lab. So they have an inclined bed of lunar regolith that will simulate the best material properties that we understand to date. We moved our AMP there to simulate the concept of operations of sun tracking and deployment of the ROSA itself at increasing levels of incline to make sure that our solution doesn't tip over on site. That was incredibly successful. We exceeded our expectations. We were able to demonstrate the capability of our platform well in excess of the contract requirements of 15 degrees. We went as high as 25 and still had stability.
And so from the Slope Lab, you guys came here.
Correct. So our mobility platform, the AMP, returned back to Pittsburgh. We then met Redwire here at Johnson Space Center Chamber A with the ROSA to demonstrate the lunar environment, survivability, and performance of the rollout solar array itself. So we'll be going down to extreme lunar temperatures as close as 20 Kelvin, and we'll be deploying multiple times and elevating the technology readiness level of this technology so that it's ready as an integrated system in the future.
Well, Chuck, we didn't even have a chance while we were there at Johnson to actually see the test take place. There were some delays, and there were other projects that were actually jockeying for position in the thermal vac chamber. But it was instantly evident that this was a different design than what we saw at Honeybee. There was no mast that you could visibly see. It was just the roll-up solar array, the ROSA, that you saw principally aesthetically. Very interesting, but different look.
It was a real shame that they didn't get to deploy down in the TVAC chamber at Johnson. We were there together for most of that week, and it was very frustrating, all the minor delays and scheduling things that we had to go through. But at the end of the day, there were several design flaws that we learned about when the article was under test, and that's why we do these tests, is to learn. Technology development is never linear. You never start with an idea and go immediately to solution that works 100% of the time. And this was just one of those hiccups. They've identified what was wrong with their system, and they are in the process of figuring out how to do the changes necessary to make it work. But I have full faith and confidence that at the end of the day, their system will work. There was a lot learned through the summer campaign of testing on the rollout solar array that Astrobotic brought to the table. There's still some work to be done, but all in all, I think it was a very successful campaign.
And again, it looks like everything's moving toward an eventual flight test, so you have some good options in figuring out what that flight test article is going to be.
As my mama used to say, God willing and the creek don't rise.
Well, Chuck, we really got some really nice test articles from both Honeybee and Astrobotic. Lockheed Martin was the other company that you all selected to get a demonstration model from. Let's take a look at what they developed.
Lockheed Martin is leveraging a host of flight hardware that we've already demonstrated and used on operational missions in space. We start with a Flight Heritage multi-mission modular solar array technology. It's flown in orbit several times. It has a mechanism that deploys a composite mast and unfurls a large solar array blanket. The challenge is taking that technology with the rest of our heritage and integrating it in a system that will operate in these very unique environments on the lunar South Pole. The second thing that we are doing is sticking it on a turntable so that when we move that deployer up vertical, this turntable can operate and track the sun. We put that in a closure that encompasses all our avionics and batteries to survive that cold lunar night, keeping us nice and warm to survive the night. And that enclosure protects us for the environments of dust. Now, We want it to be mobile. So we're working with our partner, Goodyear, and we put 4 nice lunar tires on there. But that system, all integrated, having those 4 tires support the system on inclines, hasn't been done before. So we have to auto level. So we've developed some auto leveling algorithms. So we take the VSAT, write it, and then we're able to deploy in a lunar simulated vertical orientation. And that's our solution. Everybody is going to need power. There's not one actor or activity or element that can't do its job without power. From habitats to powering up landers that need to return, to cargo landers, to mobility services. Everybody is going to need power.
So Chuck, we were able to see that Lockheed Martin was able to deploy and retract their test article outside of the thermal vac, and it worked.
Yeah, and that brings up a good question. Are they scheduled to go into thermal vac testing with their test article?
No, not at this time. It's unfortunate, but basically, much as we alluded to the problems Astrobotic had actually in the TVAC chamber, Lockheed had a few gremlins on their way to the TVAC chamber. And with all the scheduling issues, you wouldn't believe how high a demand that chamber at Johnson has for articles to go in. It's a national treasure. And so it's one of the few places that can house full satellites to do thermal vacuum testing. We haven't been able to get Lockheed Martin scheduled, but their ambient tests were very encouraging. They did multiple deployment and retractions in their facility in Denver, Colorado, and they've done thermal vacuum testing on some of their smaller pieces in order to give us confidence that they would work if they were to actually go into the chamber. There are just very few facilities where you can fit something 20 meters high and 10 meters wide in a thermally controlled environment. And so Lockheed Martin didn't have that capability within their own facilities, but they were able to test a lot of piece parts. So a lot of good work came out of that. Once again, it's a team that's ready to go to the next step. It's just, when are we going to take that next step?
With this whole call and these 3 companies that you selected and the work that they've done, you now have this plate full of options and at least ideas about how you're going to get to that flight test. So what's next for VSAT in terms of, handling that problem of power on the moon?
Yeah, it's a wonderful opportunity to have all 3 of those vendors who we think are eminently qualified to do it. And we haven't talked a lot about it, but we have our own government reference design that we built here at Langley, and that we've tested for not only the power generation capability of a solar array configuration, but we've also tested it as what we call light bender, which is the idea of power distribution. We started the show talking about how we got power down into a crater. And rather than generating the power on the surface and running a cable, you have the opportunity to basically reflect the light from the sun up at the surface down into the crater in order for somebody down in the crater to turn the energy into electrical power. So we have a whole lot of things going for us across the continuum of power generation and power distribution. But at the end of the day, we have to mature probably one more step across the continuum of whoever goes, create a flight article, and then test it. When we do that test will not only demonstrate power generation, but it will be ground zero, will be the very first element of the future lunar power architecture. It will be the 0 point for the grid, and we will go out from there, because you don't want to spend $600-700 million, $1 billion to put something on the moon for a 2-week test. You want it to last. And so our next step will be a demonstration, but it will be a demonstration that we expect to be there and actually provide power to our future elements on the lunar surface in the coming years.
I tell you what, Chuck, whether you're generating power or you're distributing power through light bender, it sounds like if we're going to be successful on the moon, everyone has to go through you.
Write that down.
Awesome. You're watching NASA Edge.
An inside and outside look at all things NASA.